All right, next up we have titrations. A titration is a laboratory technique, probably one of the most commonly used laboratory technique in a chemistry lab. You'll be doing lots and lots of titrations in this class. You'll be doing lots and lots of titrations as well in college. So it gives very good results. The equipment that we use is rather precise, and so it's just a very, very good technique to use to determine something. So here's how it works. It is a process where one reactant with a known concentration is added to another reactant of unknown concentration until stoichiometrically equivalent amounts of reactants have been added together. Now we're going to start off with acid-base titrations. We can also do redox titrations. We'll see an example of that later. But for now, we'll do acid-base titration, and that means that one of the reactants is an acid and one is the base. And so if we know the concentration of one of those substances, we can find the concentration of the other. And so how do we know when you've reached stoichiometrically equivalent amounts of acid and base? We'll get to that in just a second. The point when this occurs, where you have stoichiometrically equivalent amounts of acid and base, is known as the equivalence point. And so based on the stoichiometry of the reaction, so we got to look at the balance equation for the reaction. We can determine then what ratio is needed to either completely neutralize an acid or completely neutralize a base, whichever we're adding to the other. So we can determine when we have stoichiometrically equivalent amounts of acid and base by using a couple different things. We can use a pH meter, which is an electronic device that determines the pH of a solution, or we can use an indicator. So recall that an indicator is a substance that changes color depending on the hydrogen ion concentration, which is related to pH. So different indicators, different colors at different pHs. Be careful with this term. The point in the titration where the indicator changes color is known as the end point. So the end point has to do with the indicator, whereas the equivalence point has to do with the reaction. So here's the thing. A properly chosen indicator will change color at or very near the equivalence point for a titration. And so we're going to use that changing color that occurs in the indicator to signal the equivalence points, to signal when to stop adding our acid or base. Now, the piece of equipment that we use for a titration is called a burette. Again, it is a very precise instrument, and so it's going to yield excellent results. Take a look on page 379 in your textbooks, figure 11.1. So you see a typical setup there. So that tall tube, glass tube looking thing is a burette. Take a look at letter B in your book. Make sure you can read the volume to the correct precision. Now, it should be noted that as opposed to a graduated cylinder, which goes from bottom to top, 0 to 100, let's say, on a burette, it goes top to bottom. So 0's at the top, 100's at the bottom. And we don't really record the volume of the solution in the burette. We record the level. So take a look at the letter B. Notice we have, it looks like 10 divisions between each of those milliliters. So we have 4 and 5 I'm looking at there. There's 10 lines, so that means each division is 0.1. Those lines are pretty close together. I'm not sure if we're going to be able to read between the lines, so I think the best we can do is it's either on one line or another. So go ahead and pause the video and see what you come up with that measurement. Record that volume. It's kind of hard to tell from the picture if we can do half of the smallest division on this device or not. So I'm going to accept a couple things there. I'm going to record that as 5.4 milliliters. So it just looks to be just right above that fourth line under the 5. So again, we're reading from top to bottom. So 5.4. If we do half of the smallest division, that's between the third and fourth line after the 5. So that would be 4.35 milliliters. So again, make sure that you can read any instrument to the correct precision. So in this one, again, it's hard to tell in the picture. I'd have to see that burette in real life. Either 5.35 Better yet, because those lines are so close together, I'm going to go with 5.4 milliliters. So again, it's not how much is in there, it's the level that we record. So what you would do is you would add, in this case we're adding base to acid, I can tell by the pictures. The indicator that's being used there is phenolphthalein. Remember, phenolphthalein in the presence of a base turns pink. So you'd want to add enough base to turn that solution all the way from colorless, we see in letter A, to pink in letters C and D. And for me, that's a little bit too dark pink. We want the faintest pink possible when we're doing a titration where phenolphthalein is the indicator. So I think they just over-titrated a bit just so you could see. You really just want the lightest pink color possible. I'll show you another video demonstrating titrations later in anticipation for our lab. All right, some vocabulary terms. The solution whose concentration is known is called the standard solution. So in our lab, you're going to standardize a solution. The word standardize it means the process by which one determines the concentration of an unknown solution. So I'm going to give you some sodium hydroxide. Don't know its concentration. It'll be your job to determine the concentration of that solution. So you're going to standardize the sodium hydroxide solution. So in order to standardize the solution, we need to use something called a primary standard. So this is, as you can see there, the substance used to standardize a solution. And then the solution that you're standardizing is called the secondary standard. There is on the bottom of page 379 the criteria that make for a good primary standard. And so I believe the primary standard we're going to use in our experiment is KHP. The P does not stand for phosphorus in this case. It is potassium hydrogen phthalate. We'll see that in one of the examples in the textbook. So be familiar with what makes for a good primary standard. Make sure that those all make sense. Again, we want to pick something that's going to give us some really accurate results, something that's not susceptible to impurities, something that has a very consistent composition, very consistent composition. I think we'll leave it at that. So let's take a look at some examples of titration calculations. So now remember, at the equivalence point, you have stoichiometrically equivalent amounts of acid and base. So maybe in Chem 1 you learned this equation. Be careful, this doesn't work all the time. So here's how we read it. So it says MAVA equals MBVB. So the concentration of an acid times the volume of an acid. By the way, when you multiply the concentration of a solution by its volume in liters, what does that give you? That gives you moles, is equal to the concentration of a base times the volume of a base. When you multiply the concentration of the base by the volume of a base, what does that give you? And so be careful, this only works when the acid and base react in a 1-to-1 ratio. So a lot of times in our examples in Chem 1, the reaction did occur via 1-to-1 ratio, and so MAVA equals MBVB, that works. But sometimes we need this. So if according to the stoichiometry, if we need 2 moles of acid for every 1 mole of base, then we would have to have some setup like this. Or we could get this. So when would this be the case? Well, maybe if we had a diprotic acid reacting with a group 1 hydroxide. Let me show you an example. Now, it should be noted here, we're talking about complete neutralization anytime we're doing a titration. And so notice we have 2 moles of hydrogen ions, and they need to react with 2 moles of hydroxide ions. So 2 moles of base is needed for every 1 mole of acid. What if it were the first example I showed you? Let's take a look at that. When would this be the case? Well, maybe if you had a monoprotic acid reacting with, say, a group 2 hydroxide. Let's take a look. We have 2 moles of hydroxide ions. They need to react with 2 moles of hydrogen ions. So we need 2 moles of acid for every 1 mole of base. So those are kind of the variations that we are going to use. Let's take a look at example 11.5 and see which one we're going to use. This one is actually a little bit different even than the ones I described. So read along, please. It says, calculate the molarity of a solution of sulfuric acid if 40.0 milliliters of a solution neutralizes 0.364 grams of sodium carbonate. Always our first step here is to write the balance equation for the reaction. So take a look at that. It's in the text right above example 11-5. And so we see in that reaction, we have a 1-to-1 ratio of sulfuric acid to sodium carbonate. So this is one of the gas formation reactions. It's also acid-base type, I guess, reaction, more gas formation though. And so look at the information given to us. We're given grams of sodium carbonate. We can use that to find moles of sodium carbonate. Once we know moles of sodium carbonate, we can go to our balance equation and use that to find moles of sulfuric acid. Once we have moles of sulfuric acid, we can divide by the volume to get molarity. So I believe this problem works through moles and not millimoles. We could use millimoles, I suppose, but I think moles is more appropriate here. So make sure to divide the moles by the volume in liters, and we get 0.0858 molar for our sulfuric acid solution. That's what is needed to completely react with the sodium carbonate. All right, number 27 on page 392, same reaction, sulfuric acid and sodium carbonate. Same kind of setup. We're looking for the concentration of the sulfuric acid. So go ahead and set that up. Pause the video now, please. So here's a setup. Did a little bit different than the book did the example problem. So I just did this all in one shot. On top, I get moles of sulfuric acid. Take that divided by the volume. Notice I use 106 for the molar mass. If you use 106.0, then you have one more significant figure. So 0.0737 molar. 4 sig figs, that would be 0.07370 molar, because the rounds to 6.9 up to a 7.0. All right, take a look at 11.6 on 381. Read along, please. A 20.0 milliliter sample of a solution of sodium hydroxide reacts with 0.3641 grams of KHP. Take a look just above that, top of the page, 381. There is the structure of KHP, potassium hydrogen phthalate. You don't need to know the chemical formula, but you will need to know its molar mass. And so we'll see that just a second in the problem. Calculate the molarity of the NaOH solution. So you'll be doing something just like this, where you're standardizing your solution. You're trying to determine its concentration by reacting a base of unknown concentration with KHP. So take a look at the solution. We're given grams of KHP. We can use that to find moles, as long as we know the chemical formula. And then from moles of KHP to moles of sodium hydroxide. KHP, if you notice at the very top there, has one hydrogen that it can lose. And so, meaning it's monoprotic. And so it will react, KHP will react in a 1-to-1 ratio with sodium hydroxide. So once we have moles of sodium hydroxide, we can use that along with the volume to find the concentration. So solution is there, 0.08915 molar for the sodium hydroxide. Go to page 392 and try practice problem number 25. So notice we did go out of order in the notes. I think it said 25 first. We're going to do 25 second. It's a little different problem than that example, but go ahead and set that up. Start off with the balance equation for the reaction. Go ahead and pause the video now. All right, hopefully you figure this out. I believe I misspoke. We know the concentration of the base. We're trying to find the volume that is needed to neutralize that amount of acid. Forgot a parentheses here. we go. So take the volume of the sulfuric acid solution and multiply that by its concentration. That'll give us moles of H2SO4. From moles of H2SO4 to moles of KOH. And then knowing the moles of the base and the concentration of the base, we can find the volume of the base needed to neutralize that acid. So we get a pretty unuser-friendly number here, 0.0376 liters. So again, if I asked you to measure that out in the lab, I'm pretty sure you could not do that. What you would probably do is convert that to milliliters. So we get this much. So just a little different type of problem than we've seen so far. All right, examples 11.7, 11.8, pretty similar. Take a look at 11.7 first. The titration of 36.7 milliliters of hydrochloric acid solution requires 43.2 milliliters of standard 0.236. I should say molar. Go ahead and write that in your book. If it says milliliters, that should be molar sodium hydroxide. For the complete neutralization, what is the molarity of the HCl? So again, this is very similar to what you're going to be doing in the titration, determining the concentration of something. This time that we're using a solution of hydrochloric acid and sodium hydroxide. They react in a 1-to-1 ratio. So using the volume and concentration of the sodium hydroxide, we can use that to find moles. From moles of sodium hydroxide to moles of hydrochloric acid. And then once we know moles of hydrochloric acid and the volume, we can find the concentration. And that answer is on the top of page 383. 11.8, similar setup, except this time we're using sulfuric acid and sodium hydroxide. So this reaction does not occur in a 1-to-1 ratio. So set it up the same way. Find moles of the base, sodium hydroxide. From moles of base to moles of acid, using the balanced equation. And then from moles of acid and milliliters of acid, we can find the concentration of the acid. Answers at the very bottom of the page. All right, go ahead and try number 39 only. Let's start with 39 on page 393. And then we'll go over the answer, and then we'll go on from there. So go ahead and pause the video now, work on number 39. So I set this one up a little bit different. Something else about MAVA equals MBVB. Not only does the acid and base need to react in a 1-to-1 ratio to use that equation, but both the acid and the base must be in solution. If one of them is a solid, then we can't use that. In this case, we have a solution of hydrochloric acid and a solution of sodium hydroxide. They react in a 1-to-1 ratio. And so we get the concentration of the base, MB, 0.173 molar. All right, let's take a look at yet another different type of problem. This time we're trying to find the percentage composition. So read along with me, please. Oxalic acid, H2C2O4, or it's written here differently, is used to remove rust stains from some ink stains from fabrics. A 0.1743 gram sample of impure, so that means it's not just oxalic acid, requires 39.82 milliliters of 0.08915 molar sodium hydroxide for the complete neutralization. No acidic impurities were present. Calculate the percentage purity of the oxalic acid. So we need to find out how many grams, right? We're trying to find percentage, so percent by mass. How many grams of oxalic acid were in that impure substance? So take the volume of the base and the concentration of the base, use that to find moles. We need the balanced equation, so this reaction has a 2-to-1 ratio of base to acid. And so once we have moles of NaOH, we can use that to find moles of oxalic acid. And then once we have moles of oxalic acid, we can use that to find grams of oxalic acid. So we see that almost at the bottom of the solution, 0.1598 grams of that substance is just pure oxalic acid. The original problem is said we had a mass of 0.1743, of which 0.1598 grams was oxalic acid. So divide parts over whole, multiply by 100, we get 91.68% oxalic acid. All right, so quite a few different types of examples of doing calculations involving titrations and acid-base reactions. Hope you enjoyed that one. If you have questions, let me know. Thanks for watching.